Hello and welcome. This is the next specification video. Okay, this is obviously for Unit 4. Okay, now obviously this is the first of the A2 specification recaps. Okay, so it's going to be a little bit different to the AS ones. Okay, because the AS ones obviously we just simply had Unit 1, Unit 2, and obviously you may have gone, 2 to 4. Obviously, Unit 3, obviously, you know, is the EMPA, or ISA, even ISA, right. Okay, so Unit 4 is just going to be, on its own, it's going to be a plain and simple further mechanics. Okay, and then Unit 5 will be split up into 2 parts. I'm going to do it as 2 parts, okay, because part of the Unit 5, let me just double check here. Can do in 2 parts. Probably should have checked this before starting the video, but I'm sorry. I know it's only just started and I'm already going, what do I do here? Sorry. Yeah, I'll do it in 2 parts. Okay, so, sorry, let me get back up to where I was. Sorry. Okay, so, for God's sake, come on. Right, there we go. Okay, so, as I say, this video is simply going to be Unit 4. The next video is going to be split up into 2 parts, okay? Because obviously everyone is doing the thermal physics, so that's, you know, kinetic theory of gases and ideal gas laws, Boyle's law, Charles' law, that kind of thing, okay? That'll be one video on its own, and then the last video I'm going to do is a separate kind of for the astrophysics part of it, and obviously if I get round to getting enough free time, because obviously we all do, I'll do the other units, but I haven't really done them in as much detail as I've done astrophysics, okay, so it's pretty pointless me doing them, because I probably won't be able to give you any more information about it than what's on the specification. So I think for the moment I'll just stick with doing Unit 4 and then Unit 5 for thermal physics as a separate video, okay, and then the final video will be on the astrophysics, okay. They will all be the same specification overview kind of thing. Obviously if there's enough demand, people want me to do it, I will happily do the other units, but I mean, to be honest, the channel isn't that big and I can't be bothered, so I think I'll probably leave it, to be honest, just astrophysics. Okay, so anyway, the first thing that you do in, well, the first thing that's listed in Unit 4 is momentum. Now, it's a very easy topic, and on the new AS course, I think it is, sorry, in the new A-level course, this gives it away, it's actually on the AS spec, okay, so it shows you it's not very challenging at all. Now, the first thing that it mentions, okay, is about the rate of change of momentum. Now, we said, again, back in AS, we said back in AS, F is equal to ma. Okay, in other words, the resultant force is equal to mass times the acceleration. Well, yes, that's correct, but you have to remember, you could think of this as mv take mu over delta t, okay? Because essentially what this is, I mean, I've done this a better explanation than I've done in my actual video, for God's sake. Okay, so you know, mass times acceleration, you know, acceleration is equal to the final velocity to the initial velocity over delta t. Okay, and obviously that comes from the CVAT equation, v equals u plus at rearranged to get the acceleration. Okay, so what we did there is we said, alright, well, F equals ma, so if we put a as v take u over t, m times v take u over t, okay, expand the top bit out, so it's mv take mu over t, okay, and that gets us this mv take mu is a bit we're interested in here. This mv take mu, well, it's mass times the velocity, yes it is, the final velocity and the initial velocity. Okay, so essentially what that is, this is what the final momentum, take the initial momentum, so it's the change in momentum over, I write it a little p, so change in momentum over t, okay, obviously that gets us our equation. The resultant force is equal to the rate of change of momentum. Okay, but you don't have to say, it doesn't require you to be able to explain that, but that's how you come up with the law. And I don't think I've done that in my topic video. Okay, so anyway, that's the rate change. So you say F is equal to mv, take mu, or over delta t. Now, one of the questions you might get asked about this is you might get a force time graph for an object. Okay. Now, quite clearly, it will generally be something like this, for as far as we're concerned. Okay. So we've got a change in time, whatever it is, and a change in velocity. Okay. So therefore, what we're doing here is, if we're working out the area, we're doing force times change in time. So that's force times change in time, and that gets us this change in momentum. Final momentum take initial momentum, which is change in momentum. So this area under here is equal to the change in momentum. Okay, so that's one of the key things it requires you to be able to know on the spec. Okay, and the next little bit is simply a case of definitions, really. Well, not so much definitions, but the fact that you've got to understand what they mean by certain terms. Okay, so one of the terms it lists is impulse. Now, it may say calculate the impulse or calculate the change in momentum. They mean the same thing. So, in other words, impulse is the change in momentum. Now, it might try and trick you and say, say two objects collide, okay, object A and object B, okay, and it might say, obviously, say B was at rest and A was at a velocity, okay, and it collides with B, okay, and it says, work out the impulse exerted on B by A. In other words, work out the change of the momentum of B, which, yeah, it's just saying work out and change the momentum of B. And if it says, yeah, that's just an example. But as I say, I think I do a better job in the momentum video, if there is one. But if not, I do apologise. Okay, so that's the impulse is the change in momentum. Okay, so it's just something to be aware of. Okay, and the next thing is obviously talked about the principle of the conservation of momentum. You should be aware of that, which just says momentum will be conserved in a system as long as no outside forces act on the system. In other words, basically, if you have if you have something colliding with your object, okay, so you're considering the momentum of one object, okay, now naturally the momentum of that object is equal to the momentum of the object before. If you've got initially, there's this object and another object collides with it, and then in the after bit of the collision, you don't then calculate the momentum of that object as well, okay? So in other words, you've got to include everything you include at the start, you must include at the end, okay? So in other words, all the objects that you calculate in the momentum of the start must be at the end, even if the velocity is 0. I mean, in which case it obviously won't matter to the answer, but you just need to make sure everything you include in terms of all the objects with certain velocities and masses, you need to include in one, you need to include it before and after, basically. Okay, so that's pretty much what it's saying there. Now, you would always say the conservation is always conserved, okay? And obviously mass is always conserved as well, but that's obvious really. The next thing that it mentions is about elastic and inelastic collisions. Now the only difference, they both conserve energy, they both conserve mass, they both conserve momentum. But what is the difference between the two? That's one of the things that you need to be aware of. Okay. Now, elastic is where there is no loss of kinetic energy. Okay, that's all it means. So there's no loss of kinetic energy. So therefore, obviously, by power reduction, inelastic is where there is loss of kinetic energy. Sorry about my writing. Can't be bothered doing that much. Okay, now they're the two types of what you need to be aware of. Now it might also say what's determined by a fully inelastic collision. That's basically where at the beginning you've got two separate objects, okay, and they are moving at different velocities. Generally, the one behind will be, unless they're moving in both the same direction, and obviously this one's going a bit faster, so it will eventually collide with this object. Okay, so say it does, and then afterwards they're both moving at the same velocity. Okay, and obviously if you were calculating that, you just work out that as one big object because it'll be all travelling at the same velocity. But as I say, that's for an exam question, okay? But what this is called, is what I'm interested in, is called a totally inelastic collision. So if it asks you what is meant by a totally inelastic collision, obviously you would say, well, an inelastic collision is where there is loss of kinetic energy. The I is loss of kinetic energy, but a totally inelastic collision is just one where the objects collide and then after the collision they stay together. Now they're not glued together, obviously. Someone doesn't just rub in and go, oh, I'll put a bit of glue on there. Unfortunately not. Okay, but basically you're just moving at the same speed, so it doesn't push it away. All right. And obviously you might have to work backwards in certain questions, and obviously the kinetic energy formula is a half of mv squared, so it might ask you to work backwards. Okay, in other words, what must the velocity be for them to be moving at the same velocity? Okay, I'm not making that very obvious, but obviously the principle of momentum states that momentum has to be conserved. So even in an inelastic collision, momentum is conserved, okay? And then it asks you, okay, if they're moving at the same velocity, what is that velocity? Okay? So just use the fact that, well, momentum is conserved, and you work out the velocity, and then obviously if it says prove the collision is elastic or inelastic, whatever the case may be, it's obviously certainly 1 and 2, you just work out the total kinetic energy before and the total kinetic energy afterwards. Now as I say, if it's inelastic, those two should be different figures. However, if it is elastic, okay, then them figures should be exactly the same. Okay? Right, so that's momentum we need to know from momentum. Alright, now circulation just obviously gets you to be aware that one of the things actually is quite important. It may say, and I think it does mention in the spec there, you need to know about the fact that, actually it doesn't mention it in the spec there, but I think it's a crucial point. So this video is actually turned into a recap of each topic rather than a recap of what you need to know. But I think it's crucial because I do think it could potentially crop up as a question. I think it has done before. Now obviously velocity is a vector, which obviously means that it takes into account the magnitude and direction. Now if you do mechanics and specifically if you're reading that from last year or you're just doing it as an A2 module, okay, the direction, okay, of velocity is, the magnitude of velocity is speed, because speed is a scalar and velocity is a vector, okay, so that's obviously why you have a velocity vector. So therefore a velocity is a vector and the magnitude of the velocity is speed, okay, so you just work out the direction of speed is velocity, okay. So as I say, I do proper velocity vectors video, and you probably do need to watch that if you are an M1 student. Anyway, okay, so the principle behind that is velocity is a vector, so it's speed and direction. Now I might say if an object is moving at a constant speed, it's crucial, okay, in a circle, is it accelerating or is it not accelerating? And the answer to that is accelerating. You may go, how the hell is it accelerating if it's moving at a constant, if it's moving at constant speed, how the hell can it be accelerating? Remember, velocity is something that takes into account magnitude and direction. Well, it might be going at the same speed, the same magnitude, but if the direction is continually changing, we just assume to be continually increasing, okay, it will be increasing, okay, so that's just a brief. Now I'm not going to write that down because, as I say, it doesn't really mention it in the spec, and I'm pretty sure that's because it's something you should remember from GCSE, but I haven't seen a question on it, so it's worth mentioning. Okay, so obviously you need to be aware of the centrifugal acceleration formula. A is equal to v squared over r. Now there is a proof behind that, but you don't need to know it. And as this is only a recap of the spec video, I would go explaining that, but I don't want to waste too much of your life. So as I say, that's given to your formula sheet, so just apply it to questions, etc. Now this velocity is obviously, it is shown in the formula sheet as this weird sigma thing sign, which is angular velocity times the radius, okay? The angular velocity is given by 2 pi over the time period, or as you know, the time period is one of the frequency, So therefore, the angular speed is also calculated as 2 pi times the frequency. Okay, and if you times that by the radius, you get the velocity. Okay, so you just need to be aware of that, and obviously it might end up combining this equation with this equation, obviously to get that's a velocity along the circumference, and generally it's going to ask you to calculate the angular velocity, because obviously that takes into account the angle, whereas that just takes into account obviously on the circumference. So basically that just takes into account, say if you're at the centre of the circle, this takes into account if you're on the circumference, because obviously it times it by the radius. Okay, hopefully that makes sense. Now again, the next thing, obviously it's really quite obvious, again we like using F equals ma at the start of this. Okay, well, as you know, the resultant velocity equals mass times acceleration. We just said acceleration is velocity squared over the radius. Okay, so sub it in. F is equal to m times v squared over r. Okay, so therefore F is equal to mv squared over r, and that's the centripetal force. Now, if it says what's the maximum velocity that a certain object can move at, okay, and it might give you the velocity or whatever, you just make that, you know, that's going to be, your force will be at a maximum, and it will, basically, I'm not explaining it very well, but as I say, F equals mv squared over r, that's the force, and then it's obviously going to get to a maximum before it slides off, and it will apply to whatever question you're looking at as to how you answer that. So just be aware of the fact that you can use that to explain the maximum force, okay, the limiting force of friction, because that's a centripetal force, so therefore it's obviously going to be equal to the force trying to pull it out at some point before it eventually spins out and you die. Okay, so yeah, as I say, it mentions that how you get to that, it won't be asked, but as I say, I probably will do a video on it at some point because it isn't that bad. It's really just about similar triangles and working it out in a circle, but as I say, you don't need to be aware, and to be honest, I think A2 physics is confusing enough without you worrying about things you don't need to work out. Okay, so that's pretty much, as I say, I will be doing a video on that because it isn't too bad. Alright, so that's all about circular motion. Next, dreaded one, people find quite annoying, and to be honest, I don't really think it's that bad. I mean, I think the questions are bad, but I don't think the actual theory is that bad. It's just how they manipulate the wording, the questions in this. Okay, it's a simple harmonic motion. Now, you may go, what the hell is a simple harmonic motion? And if you've done the course and you're asking that, I might be a little bit worried. But as I say, you know, I don't really care. So there's two things. The first thing it mentions is about there's two principles for simple harmonic motion. Okay. Now, you could go on to explain, well, you know, the velocity is at a maximum, the equilibrium position, blah, 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 blah. But the two things that you need to state when it says, you know, it might ask, what is meant by simple harmonic motion? And when it asks that, you have to state the two features of simple harmonic motion. And the first one is acceleration is proportional to displacement. So at the maximum displacement, there's a maximum acceleration. You go, well, the velocity at the maximum point displacement is 0. Yeah, well, that's because it goes from a negative velocity to a positive velocity, and that's going to be the biggest change. Okay, so therefore acceleration is directly proportional to displacement. That's your first point. Okay, I probably might have actually included my second in that. Oh yeah, and the next point is acceleration is in the opposite direction to displacement. Okay, so acceleration is in the opposite direction to displacement, and that's kind of what I just mentioned already. Okay, now obviously simple harmonic motion can either relate to springs or it can relate to pendulums, but I think pendulums is one that they use quite a lot. Now again, the next few points it mentions is just about being able to, it just shows you a few formulas. Now these formulas are just, again, given in the formula sheet, and any question you get on these generally is about working out, you know, the velocity, the acceleration, or using it to work out the kinetic energy. In other words, very, very simple rearranging of these equations. And I think what it's trying to get across at the spec there is simply you've got to be able to understand what the individual parts of the equations mean. Okay, so I'll just list the equations for you now. Okay, so the first equation is acceleration. Now we know acceleration is opposite direction to displacement. Okay, so it's negative 2 pi times the frequency all squared. So it's negative and then times that all squared. It doesn't turn positive because the negative's outside the brackets. Okay, and that's times the displacement. Okay, times x. Now, because acceleration is a positive maximum, okay, this equation here, negative 2 pi f squared, obviously that you could change that to 2 pi over t, and obviously that comes from the velocity, because obviously you know the velocity, that comes from the angular speed. So basically acceleration is the angular speed squared times displacement, because it's directly proportional to displacement, and you could say therefore the constant proportionality is the angular speed. That makes sense. If it doesn't really matter, you just need to be able to understand what that equation says. Okay, so the angular speed is 2 pi over t, or 2 pi f. Okay, now as I say, the acceleration is a maximum at the point of maximum displacement. Okay, and if we're talking about, if we go to the pendulum idea again, it's going to be a maximum at its amplitude. Okay, so this displacement here times x, obviously this won't change. Okay, the angular speed won't change because it's a constant as implied here. Okay, so therefore this x, this displacement, will be a maximum when the x equals a. In other words, the displacement is equal to the amplitude. In other words, when the object is at the maximum amplitude, it will have the maximum acceleration. Okay, so hopefully that makes sense. And that's kind of why that formula exists like it does. But as I say, all you need to be aware of the fact that x represents displacement, 2 pi over t, or 2 pi f, okay, and represents angular speed. There's a negative there, and the angular speed is squared, but remember the negative is outside the square brackets, so the acceleration will be negative. Okay, the velocity, now you don't need to know how you derive this, okay, it doesn't specify. Again, it's just about being aware of what bits of the equation mean. Now, I think I've actually done a simple harmonic motion video, and I think I do explain how you get to this. I'm not exactly sure if I have, but if I haven't, I will be doing a video of how you get up to this. But as I say, you just need to be aware of how it's of what it looks like. Okay, and as I say, they are given to you in the form of the sheet, so really it's just a case of knowing what the bits mean of it. So it's 2 pi f, in other words, again, the angular speed, plus or minus the angular speed, because obviously what direction you're talking about, okay, times the square root of the amplitude squared, take the displacement squared. Okay, and this obviously proves the fact that the velocity is at maximum at the point 0 displacement, okay, because obviously this 2 pi over f doesn't change, okay, but this a squared take x squared, well, this is the amplitude, obviously that doesn't change, but the displacement does. Okay, so the displacement 0, this square root thing is going to be the maximum, this is a constant, so the velocity therefore is a maximum at 0 displacement. So you can see how you can use these equations to actually work out, okay, you look at the equations on the formula sheet, it says where is the velocity of a pendulum a maximum. You just look at the equation for velocity and say, well, I know that x is displacement and a is the amplitude, okay, don't get that confused with acceleration, that's big A. Big A is the amplitude, okay. Yeah, so you just look at that and go, well, it's when because obviously that's not going to change, well, just for a hypothetical situation. Generally, unless it specifies it won't do, okay, but don't get confused on that, just think, well, obviously if x is 0, that's going to be the biggest, okay, so the velocity is maximum at 0. Now, rearranging this, okay, to get the displacement, I don't know if that's exactly what you do, but anyway, the displacement is equal to a, the amplitude, times the cos of 2 pi ft. In other words, it's the angular velocity times the time. Okay, now don't ask me how you come up with that, because I'm not going to go through it in this video. But anyway, you just need to be aware that this x is the displacement, that is the amplitude, and this is the angular speed times time. So it might just give you the angular speed and the time. You've got to realise that's the same as the angular speed times the time. Okay? But as I say, you just simply need to be aware of how you use them equations. Okay? But as I say, I've given you a bit more information than I probably needed to when I'm just as this video is just simply going over the spec and ruining your life. Okay, but as I say, you just need to be aware of how they work, and you can see how from using the velocity and the acceleration equation, how you can therefore answer questions without actually having to remember the knowledge. But as I say, hopefully you just actually revise and know that anyway. Or maybe I've just insulted you, you have revised and you forgot it. Okay, so the next thing it mentions is about the displacement graphs, velocity, acceleration and displacement graphs for an object in simple harmonic motion. Now, as I say, you could look at that from the case of a pendulum or a spring. Because they're both in simple harmonic motion, the graphs for a pendulum and a spring, okay, in the case of velocity, displacement and acceleration, they're all going to be exactly the same. Now let's use the fact, because I was using them equations there, we said that the velocity, okay, so V max, that's velocity at maximum, is when the displacement is equal to 0. Okay, so when it's at its equilibrium position, in other words. The acceleration, however, the AC, which means acceleration max, occurs when the displacement is equal to the maximum. Okay, in other words, it's maximum displacement. Now, there's no rule like this for talking about displacement, because obviously displacement is the first line that you draw. Now, obviously, it's going to give, because we talked about the displacement as x is equal to a times cos of 2 pi thingy. It's going to be a cos graph, but obviously cos and sine graphs are the same, but they're just displaced by 90 degrees. Okay. Yeah. So what we've got here is we can use this to, because all these curves are going to give different cos graphs. They're just going to be displaced by different amounts. Make sure I've got my graph for this. Okay. So the first thing. Basically, when you draw curves for it, as I say, it's going to be a sine curve. So the first thing I would draw is something like this, where we've got a horizontal line. They may have drawn it for you, and obviously this is going to be a positive, and that's going to be negative. So whatever curve it is, obviously this will be the negative part of it, and this will be the positive part of it, will be the negative part of it. Okay. So the first thing that I'm going to start with is the displacement graph. Line, okay? Now, as I say, this graph may look slightly different for whatever it's telling you to do. Now, the reason for that, okay, is because the velocity graph and the acceleration graph is related to each other and they're therefore obviously related to displacement, okay? So, where do we start with the displacement? Do we start it at 0? Do we start at positive? Or do we start at the negative? Now, they will tell you that, and whatever thing they tell you, okay, start at positive, negative or 0, is going to have an impact on what this graph looks like. Now, if they start it at 0, then they will obviously have to push it up to the maximum, okay? Because if you just put it at the equilibrium 0 and then just leave it there, it's not going to start moving by itself, okay? So if it starts at 0, you assume it's already been moving, okay? So therefore it's at its fastest point. Now, for this example, I'm just going to assume it's been released from its maximum point. In other words, the displacement, okay, actually, good, I've got a few different colours here. I'll do the displacement graph, okay, in red. Okay, so as I say, it will start from a positive point. Okay, so it will start. So it will look something like this for displacement. Okay, we'll do 1.5 cycles. As I say, they may ask you to do more cycles, in which case obviously you draw more. Now, I've not drawn this very well because I'm just doing this freehand. Okay, so these two peaks here should be exactly the same, and if they're not, then it's just my crap drawing. Okay, so that's the displacement graph. Key to point out where this is, drawing the point where this is positive, sorry, drawing the point where it goes through the nodes. Okay, and see, plot on the, now obviously it doesn't appear to be so relevant at the moment, but it's a good idea at this point when you first draw it, okay, obviously the first graph you're going to draw for this is a displacement curve, okay, so you plot on the points, on the x-axis if you want to call it that, where it's at a maximum. Now obviously there's no point plotting when it goes through the x-axis because it's kind of already done that by going through the x-axis, but it's helpful for the other curves we're going to draw to plot on where this is a maximum and a minimum. Obviously, don't actually plot it on the curve, but plot it on the x-axis. Again, if you want to call it that. So it's up to you whether you draw the velocity graph next or the acceleration graph next. But again, we need to use these principles to say, yeah, well, when the velocity is at maximum, the displacement is at 0. So in other words, the velocity is at maximum when this curve cuts through the x-axis. Okay? And as I say, obviously it's either going to be a positive maximum or a negative maximum. But we'll go into that in a bit. But you just have to remember when the displacement is 0, this velocity graph is going to be at maximum. So it's going to be either here or up here. Sorry. Kind of giving away. I've got some notes here, obviously not doing off the top of my head because I'm not that clever. Yeah, so when it goes through the x-axis, this displacement curve, the velocity curve is going to be at a peak or a trough here. Okay, and obviously that will be related to whatever type of graph you're looking at. Whereas the acceleration graph, okay, it's going to be at a maximum when the displacement's at a maximum. Now obviously it's not going to be exactly following the displacement curve, okay? So you'd say, well, when this is at maximum, the displacement is at maximum. So obviously the acceleration will be up here when this is down here, otherwise you'd have the same graph, okay? So you can think of it like that, you think of it, well obviously when the displacement, you're going to have a negative acceleration, okay? So I think the acceleration graph is probably the easiest one to draw on. Now, as we say, the acceleration graph is at a maximum when the displacement is also at a maximum. So the acceleration graph is going to cut through, basically what I'm saying here, it's going to be at peak when the displacement graph's at peak, and when it's at 0, in other words, when it cuts through this x-axis, if you want to call it that, the acceleration graph will as well. So basically the acceleration graph will cut through the x-axis when the displacement graph does, but it will almost be like a, it always look like when you're drawing a stationary wave thing back in Unit 2. Okay, that's what this first bit will look like. Okay, probably draw it in green actually. The acceleration graph I'll draw in green. Now, using the principle that the acceleration is at maximum, basically it'll follow this curve and it'll look like this. Okay, so make sure I'm doing this right. Okay, so it'll start from down here, it'll cut through here, and as I say, you may want to plot on the points just so you can kind of join them up. Okay, so this might not be exactly perfect, but hopefully you get the gist. Sorry, I do apologise. Right, apart from the fact mine doesn't quite cut through there, it should do really. It's a bit better. Sorry about that. You get the principle. I've kind of explained it, so hopefully my drawing doesn't make it that bad. Okay, so all we need to do now is draw on the velocity curve. Now, as I say, that's why it's a lot easier drawing on the acceleration curve. Now you could go, yes, well the gradient, sorry, the velocity is the derivative of the acceleration or whatever it is, and use that to say the acceleration curve is the derivative, the gradient of the acceleration curve, or vice versa. Okay, I mean obviously that's going to be helpful if you do M3. I'm not sure if you do, but in which case obviously you could therefore just use the principle that obviously the derivative of acceleration is velocity or whatever it is. I don't know, to be honest, at this point in time. But as I say, it's a lot easier just think of it like this, I think, rather than trying to remember that. Because you can just use these points. As I say, you don't even need to know about this. You just use them because we got these ideas from them velocity and acceleration equations we were given in the formula sheet. So you can work all of this out, even this curve, just from them equations on the formula sheet. So they've basically given you the answers on the formula sheet, which I think is really nice. But obviously, they've done it in a way where you've got to know what you're looking for. I mean, that might be a lot of bollocks to you, but hopefully you understand what I'm saying. Okay, so we've drawn on the acceleration graph and the displacement graph. So obviously the last graph we're going to draw on is the velocity graph. Now, going back to the idea that the displacement, when the velocity is at maximum, the displacement is 0. Okay? So in other words, when it goes through the x-axis here, this velocity curve is going to have a peak. And when the displacement graph has a peak, this velocity curve is going to be 0. Okay? So as it starts off at a peak, okay, we assume this to be a peak here, it's going to start off at 0. Okay? And again, it's going to be a cos graph because they're just different phases out of each other, out of phase with each other. Okay? So because it's not going to go up here, okay, it's going to go down there. Okay. So I just draw it. So it's obviously this is a peak when it's at the this is going through the x-axis, and when this is a peak, it goes through the x-axis, and so on. So it will look something like this. Okay, and obviously that's going to be a peak. So it looks something like that. Okay. Now obviously, most likely on the exam, this will be scaled out in terms of time, but I couldn't be bothered. And to be honest, the principle, that's just the principle that you need to be aware of. Okay. Right. Is there anything else? It says that the velocity is a gradient of the displacement time graph. So basically, the velocity is a gradient of the displacement graph. And yeah, what does it say? You don't really need to. Just easy to remember it like that. Okay. So that's the simple harmonic motion of a pendulum. Okay. Now the next bit goes on just to make sure you can distinguish between the two equations for a time period of a pendulum and the time period of a spring system. Okay. Actually, I want to pause the video because I just want to have to draw some little annotation dots to make myself seem that little bit more clever. God's sake, clever. shows how clever I am by saying cleverer. But anyway, I'll just give you a second if you want to copy that down, and then I'm going to move on, put some nice little annotations on the board for you. From AS Physics is force times distance, okay? And it's just a case of either apply F equals mg to this value of F, in which case you would get your gravitational field strength equation, or if you applied Newton's law of gravitation to that equation, you will get the gravitational potential equation, it's Gm over R. Okay, and remember, this is the energy needed to escape the planet. Now, the gravitational force of the planet, gravitational field of the planet. Now, because there's so many planets in the universe, theoretically, even before you leave the gravitational field strength of a given planet, you'll more than likely be attracted by another gravitational field strength of another planet. So really, you can never truly escape it. Okay, because there's always some gravitational force somewhere in the universe. Okay, so the next thing it mentions is about is the last bit of so that really was the hardest part of gravitation, really just rearranging some equations, understanding the equipotentials, etc, etc. Okay, so the next thing it mentions is that the students need to be aware of circular orbit, okay, energy conservation for an orbiting satellite, but hopefully they're self-explanatory. So basically what it means is, because obviously if we're talking about a satellite orbiting the Earth, okay, what they might do, and as I was saying, what they might get you to do is combine your knowledge of circular motion, so all your circular motion equations, which hopefully you're all aware of because we've been through that and I don't need to go through it again, okay? Because if we have a satellite orbiting Earth, it's obviously going to be orbiting in a circle. So it might ask you to combine the velocity, the angular speed, anything like that, okay? With all of these equations on here. Now I'm not going to do that because obviously there's so many different things they can ask and combine with. I'll probably spend a whole other 2 hours trying to explain that to you. So I think what's probably better is simply just going, yeah, you can do it yourself if you want to, but I think when we go to look at past paper questions, okay, it will be more specific, okay, but I'm just saying you need to be aware of that they might combine the circular motion equations with gravitational equation, with the gravitational stuff, okay, like that. But as I say, that's very kind of self-explanatory. Alright, so that's really all there is for gravitational fields and gravitational fields. Now we're going to go on to look at electric fields. So I'm just going to pause the video and I'll sort this all out, okay? Because I want to draw some extra stuff on the board before we continue. So what I've drawn on the board here is the two equations that you need to be aware of. And I mean, you're given them anyway in the formula sheet. Okay, But one of the things it mentions, just need to know the distinction between the and which one, in terms of which one you use for a pendulum and which one you use for a spring, okay, and what the individual bits of the equation mean. Now, I think it is given in terms of, it tells you this is the time period for a mass spring system and this is the time period for a pendulum, okay. Now, it's very easy to distinguish because this K here is obviously a constant, but it represents the spring constant, therefore it's obviously going to be to do with the spring time period, okay? And this one is obviously, because it's the other one, well, you don't really have a length, well, technically you do have a length of a spring, but there's no spring constant in this one, so obviously that's the other one, that's for the pendulum. I mean, I think it tells you anyway, but you just need to be mindful of what they mean, okay? So obviously this is the mass of the spring system, okay? Or what's displacing it, okay? It will tell you the total mass. K is the spring constant, obviously. L, okay, is the length of the spring, and G stays the same. It's, well, obviously, if it's on Earth, it will be 9.81. Now, it might say something about comparing a time period of the pendulum the same length on Earth and on on the Moon, okay? In which case, you just think, well, this G is going to be smaller, so therefore this square root is going to end up being given a larger number. Okay, so the time period will be larger. And obviously you need to be aware of the fact that time period is 1 over the frequency, so you may want to rearrange this equation to get it in terms of doing 1 over that equation. Although what I would recommend is simply just saying, working out the time period and doing 1 over that, rather than trying to rearrange this equation and probably getting something wrong. Okay, so that's the time period. Sorry. Next thing you should be aware of is the energy that's associated in terms of an object in simple harmonic motion, different energies, okay? Now, there's this equation, the total energy, okay, in the system at any one point is made up by the kinetic energy, obviously, plus the potential energy, EP, okay? And at any given point, that holds true, okay? Now, the amount of kinetic energy and potential energy is different, okay, obviously. Now, going with the theory that kinetic energy, obviously, the only determinant really of kinetic energy is the velocity. Well, obviously the mass is part of the equation for kinetic energy as well. But obviously we assume that doesn't change, okay? So, the kinetic energy is made up by the velocity. Now let's just think of that a little wavy thing I had on the board there, graph, that's the word. And in that graph, we said, well not in, I didn't go inside the graph and go, oh, I say this. No, when we were describing that, okay, we said that the velocity was a maximum at the equilibrium position. In other words, how does it relate to the potential energy? Well, the potential energy, the only thing you really kind of, knowledge straight out your mind, mg times delta h, okay? Well, it isn't that, but if, to have explained it well enough on here, this potential comes from kind of, I mean, you can think of it as like that, okay? In terms of the fact that, you know, so when we've got the pendulum here, and then this dotted line represents its maximum displacement, obviously this height here, and this height here, there's going to be a certain change in height which will relate to this, okay? Hopefully that makes sense. If it doesn't, I mean, it's really just basic knowledge, to be honest. Okay, just basic AS knowledge. It's quite, it's my explanation. Okay, so when the kinetic energy is a maximum, this is going to be 0, and when this is a maximum, this is going to be 0. Okay, and obviously, you know, when it's halfway, they'll both be halfway, etc., etc. But the principle is, the potential energy will be a maximum at the maximum displacement, whereas the kinetic energy will be a maximum at the point of 0 displacement. Okay, so it's kind of quite similar to that graph we drew. Okay, now this, I'm not 100% sure, it doesn't, I mean, it says you're supposed to know the relationship between these three components, okay? It doesn't explicitly say you need to be aware of this graph, although I think you probably do, okay? So this top line here is the total energy, ET, okay? This line here, basically the box, the top of the box is ET. Okay, you can say the bottom of the box is ET, but that where it's ET is 0, you can say this is where ET is. But it doesn't matter, actually, probably, I mean, you don't need to. Okay, so if we start from the point of maximum, one sec, I'll draw the curves actually and I'll explain them. It's probably not the best though. you get the idea. It should be just a normal curve that goes through. Oh, for God's sake, that really hasn't gone very well. Right, I don't know if you can see that very well. In terms of where, well, obviously you can see, hopefully you can see it. This green curve I've labelled as EK, and this obviously red curve I've labelled as EP. Okay, now basically they will all, at any given point, they will add up to this straight line at the top. They will combine, okay, to one of the lines. So see this line at the bottom, you could say that's the total energy at any given point. Okay, these two curves have to add up to sorry, one sec. I think I'm missing out a line there. Sorry. I'm not the genius that I obviously think I am. Sorry, do apologise. Come on. Sorry. I think I'll start apologising now. Come on, where is it? No, I'm not. Yeah. Well, maybe this one. 0. Yeah, sorry. So this is the total energy, yeah. Okay, so at any given point, these two will add up to this line. Okay, you can see that makes sense in terms of the kinetic energy will be a maximum. Okay, you could say this is a maximum and this is a minimum. This will be a maximum when the other curve is at a minimum, because obviously the kinetic energy is a maximum when the displacement is 0. When the displacement is 0, the potential energy EP is at its lowest. Okay, so I mean, really, this EP doesn't relate to gravitational potential, but I just try to familiarise you with that if you want 100%. What it actually relates to the potential energy. If it asks for this, by the way, I probably shouldn't have put that gravitational potential in there. If it does relate to potential energy, it will be talking about the potential energy in terms of how far it's been stretched, how much energy is put into it. Okay, so that really EP, in other words, is the elastic potential. That's the key thing to take away, really. It's the elastic potential. Okay, so elastic potential really is okay, I think the best thing to do. Now, I do a better explanation of this in the proper video for simple harmonic motion. Okay, so we've got a force against extension graph, and as you know from Hooke's law, we should get a line with a constant gradient. Okay, and now the energy under that line is the potential. Okay, so you could either say that's a half times F times delta L. Okay, or you could say it's a half times K x squared. Okay, so either one of them two equations. I'm going to go with this one because it fits into the explanation that I'm going to do just now. Okay, so half of kx squared is the energy absorbed or taken in, put into the spring, getting up to a certain point. We'll just call it this point. Now, as I say, you could say that area is equal to half times F times delta L, but that just doesn't particularly work for this explanation. Okay. Yeah. So that's the potential energy equation. Now you should know the kinetic energy equation, okay, is a half of mv squared. Okay, but obviously I'm going to need to alter that just a little bit. Okay, now because I'm going to be looking at this in the context of the spring system. Okay, so really the mass. So best way of so that is the kinetic energy. Now we want to put that equal to something. Now we know the total energy is equal to the kinetic energy plus the potential. So therefore you could rearrange this equation to say the kinetic energy, K, is equal to ET minus EP. Okay, so it's just a simple rearrangement of that equation. And we know the potential energy is equal to that. But the total energy at any given point, in other words, when this is a maximum, okay, it will be equal to, basically at any given point, you could say it's a squared take x squared. I think I'll probably do a better explanation of that in the proper video. Okay, so that is equal to ET take EP. Okay, so therefore that's equal to EK. Okay, so a half of mv squared is equal to half k a squared take x squared. Okay. I'm probably not doing this very well. Yeah. Okay. Sorry, I'm just having a bit of a, just trying to get my head back to it. Yeah, so if we times both sides by 2, we'll be left with mv squared is equal to k a squared take x squared. Okay? So what you would do there is you rearrange this to get v, okay? So, would you? Sorry. K over m. Yeah, so you rearrange that to get v, so you get k over m. Actually, no, I'm not going to do an explanation because I'll probably do something wrong. Because I've not done the proper preparation for this, as you can probably tell. Yeah, I'm sorry about that. But as I say, I'll do a better explanation in my proper video. This is obviously a fake one. And in the video for simple harmonic I do a better explanation of this. I mean, to be honest, the reason I'm being so crap is because I've actually not generally prepared for this kind of stuff. I have, but I haven't looked over this again because it does take a bit of looking over it. It's very hard to just remember the formula and the process you go through. I mean, I think the only thing you need to be aware of, what I was going to end up doing, just for those of you just wondering what the hell I was trying to do, was get the velocity equation, okay, for an object in simple harmonic motion, okay, which I probably shouldn't have attempted because as I say, this video is just trying to show you what you should know. So sorry about that, but anyway, I've recorded it now, so I can't bother taking it out. And there's worse things I forgot to take out, so it's alright. Okay, so anyway, all of that was just trying to show you need to be aware of what these two equations mean, okay, what the individual bits of the equation mean, and the relationship of that equation, okay, and that graph is obviously quite important as well. Okay, so if you get that graph and that equation in terms of what the potential is, okay, these two equations and what the individual parts of the equation means, you should be fine. All this was just me being a complete and fucking arse, okay, getting it wrong. Okay, so I do apologise about that. So the next bit is going on about, just make sure, force, vibrations and resonance. I'm going to make that right. Okay, so what it mentions here is just going over all the characteristics that are associated with force, vibrations, resonance and free vibrations, all that kind of crap. Okay, so the first thing it mentions, okay, is about free vibrations, okay? And what the hell is a free vibration? I mean, to be honest, in this little last bit of SHM, all you really need to be able to do is explain what is meant by free vibration, what is meant, etc. Just defining the terms, really, because we've done all the maths. Well, I didn't, I fucked it up, but the rest of the maths was pretty simple. Okay, a free vibration is simply when the object oscillates, okay, you can obviously in SHM, so it's when the object oscillates in SHM okay, with its natural frequency. In other words, if you pulled it back to its maximum displacement and just simply let it go and didn't touch it until it stopped, it would be classed as a free vibration, okay, with its natural, so it operates in when the object oscillates in SHM with its natural frequency, okay, it's assumed to be a free vibration. Or you could also say, as a definition for that, it's just an object oscillating in SHM without an applied force, okay, or it oscillates in its natural frequency. I think either would be acceptable. Force vibration, on the other hand, therefore, is kind of the opposite. You're still operating in. Sorry, I keep saying operating. Stupid idiot. Free vibration is when the object oscillates in. Got that one, right? When the object oscillates in simple harmonic motion, etc. I just put a squiggly line because I can't be bothered right now again. Okay. When it oscillates at a frequency. Just get my wording right. At a frequency determined by an applied force at constant intervals. So it's a force vibration is when an object oscillates in SHM at a frequency determined by a constant applied by an applied force at constant intervals. By an applied force at constant intervals. Sorry about the noise. It's yeah. Anyway, right. Okay. So that's free vibrations and force vibrations. Just as I'll be banging my head into that wall to try and, you know. Anyway, so the big thing here, the next thing is kind of what all of these are trying to build up to. There's this thing that I can't say properly. It's called resonance. And basically, what happens here, all you need to know, there's two things. When it asks for the definition, now obviously you can define force vibration, that's pretty easy. It's just when an object oscillates in SHM with a frequency determined by an applied force at constant intervals. So the two things you need to mention there is obviously, well, this bit about oscillating in SHM is just introduction to it, okay? But this bit afterwards, especially the bit that I've underlined here, is crucial, okay? You need to mention applied force and it's at constant intervals. So if you just mention applied force, okay, it's going to be if it's applied at different intervals. If it's applied once when it's at maximum displacement and once when it's at minimum displacement, it's going to give. It's going to be oscillating with different frequencies at any one point. Okay, so it's going to be. You need to be at constant intervals. Well, this resonance, basically, obviously you need to be aware of the definitions of natural and a natural frequency. Okay, now natural frequency is just the frequency that it oscillates at without any outside forces acting on the system. It's very easy to say for that. Well, it's natural frequency. Well, you're just repeating what the definition says, and that's not right. Okay, obviously it's not going to be that easy. Okay, so the big thing here with resonance is when the applied frequency, okay, which is pretty much what this is all underlined. So if you wanted to define applied frequency, basically what I've underlined there. So applied frequency is when the applied frequency is equal to the natural frequency of the system. In other words, you're causing a frequency of the system which it would naturally have if it was left to oscillate without any forces involved. So it's, when it operates, it's natural. When the applied frequency is equal to the natural frequency of the system. Okay, and if it was a 2-mark definition for resonance, then that will get you 1 mark. The next point you need to mention when you're defining resonance is about the fact that this causes the biggest amplitude. Because it's almost like, I think the best way I think of this is it's almost like when it would be oscillating at its natural frequency anyway, but you're doubly pushing it as soon as it gets to its natural, when it would naturally turn around, okay, when it would actually change direction, you're changing direction. So it's like the force of it changing direction itself due to gravity and the extra force you're pushing into it sort of doubles up the amplitude, so has a big amplitude. Now, maybe that doesn't make sense, but as I say, you only need to be aware of the fact that it's when the applied frequency is equal to the natural frequency, and it's where the biggest amplitude takes place. Okay, so that really was the last bit on SHN. Okay, the next part of the specification, obviously, next bit that I'm going to talk about is all about the fields. Okay, now I'm going to start off with gravitational fields purely because I think it's an easier introduction, okay, to fields, okay, and obviously that's what comes up next in the specification. But also you have to be aware that electric fields are pretty much identical. Now I'll go through the similarities and differences once we've gone through both of the fields, but I just want to bring up something at this point, okay? If you're ever stuck and you think, oh my god, I can't remember the similarities and differences between the two, I mean obviously hopefully you will do. But the key thing to make distinction, now pretty much they are identical, okay? Obviously gravitational potential and electric potential, obviously in the context of their different fields, whatever question you might be asking, but pretty much they are identical. The types of fields are identical, okay? Now obviously we'll go into a bit more detail of examples, but really you can just think of any equation. If you don't think, oh, what's the electric field equation for that? The gravitational constant will be replaced by the obviously K, the constant in electric field, which is 1 over 4 pi epsilon naught. Okay, now you could just remember the answer to that because this epsilon naught is a constant, and obviously 4 pi is a constant as well. Okay, so they replace the gravitational constant with the constant in electric fields, and then they replace the mass, okay, with charge. Okay, but obviously there's more similarities and differences that are probably more scientific you'd want to list if it asked you for similarities and differences. But really, in terms of equations and pretty much everything, they're what I class as kind of the main and easiest things to remember, to be honest, in terms of using equations. So making sure you're using the right equation. Okay, maybe that helps you. Maybe it doesn't. I don't know. Help me anyway. Okay, so the next thing it talks about is the first thing in gravitation. Okay. Gravitational fields is about Newton's law of gravitation. Okay, now it's very easy just to state it. Okay, if it says, you know, define Newton's law of gravitation. Okay, you may just go, well, we'll just state this: F is equal to G m1 m2 over r squared. Okay, well, no, you need to be able to build it up, and that's what this bit in the specification is saying. You need to be able to build up this equation. Okay. So it's almost like a little paragraph that you have to learn. Okay, this G, remember, is a constant. Now, in this case of building it up, that G will kind of represent a constant of proportionality. Okay, now there's two types of proportionality. There's inversely proportional and directly, and we're going to be using both here. Okay, so build up this summation. Now, it doesn't matter obviously which one you do first. It's irrelevant, obviously, because it will build up to the same equation. Okay, so the first thing you would say is the force, the attractive force. Remember, this is always attractive, that's one of the things. Okay, the gravitational force will be directly proportional to the sum of the masses. Okay, so it'll be directly proportional to m1 times m2. Okay, the next point you need to mention is that the force is inversely proportional. I show is this is the fish symbol to 1 over whatever it is you're doing it to. Okay, so it's inversely proportional to the square of the separation. Okay, so them two are two things that you would state. Okay, now I don't think it mentions anything else about building up this equation. Okay, but the next thing I would say, okay, so if it asks you to define Newton's law of gravitation, yes, you do state it, but firstly, what I would do, and I think this is what I was trying to mention in the spec, is these 2 points. Okay, so you say that the force is directly proportional to the sum of the masses. Okay, and by sum, obviously, you could say multiplication of the masses. If it makes you feel more confident that you're going to get the marks right. Okay, the second point is about that the force is inversely proportional to the square of the separation. Now, don't put it's directly proportional to 1 over the square of the separation, because that's saying it's inversely proportional to the square of the separation. Okay, so it's not directly proportional to 1 over the square of the separation. That is just saying the force is inversely proportional to the square of the separation. Now, I'm not 100% sure you need this next little bit, And if you just remember them two, that's perfectly okay. This next point is just simply, I would just add in that these two obviously are going to result in a constant of proportionality, because obviously when something else is directly proportional to something else, okay, it's going to be equal to this times some kind of constant, okay? So you say in both cases the constant of proportionality is g. You'd state the constant proportionality, which is obviously a gravitational constant, and then there's no harm at all in just stating what the value of g is, which obviously you could just look in the formula sheet for, which, if you're out of interest, is 6.67 times 10 to the minus 11 kilogram squared per meter squared, I think. I have to go back and double check that. Okay, but anyway, that's the principle. Right, so as I say, you just really need to be able to explain this. So if it was a definition question asking you to find Newton's law of gravitation, you would build it up as this, okay? So you would say it's directly proportional to the square as the sum of the masses, inversely proportional to the square of the separation, and the constant proportionality is g, the gravitational constant, and therefore state it, okay? So that's one of the things you need to be aware of, okay? That's the first thing it mentions, okay? Gravitational field strength. Now this is quite easy really the first bit of it is anyway, okay? So it comes from the fact that the idea, again of Newton's law, but not Newton's law of gravitation, in the sense of the one we just looked at. It actually comes from F equals ma. Now, in free fall, you obviously would have been told that the acceleration is equal to the acceleration due to gravity. In other words, the acceleration is equal to little g. Now this little g, they may have just said, that's the acceleration due to gravity, but more specifically, that's the gravitational, let's make sure I'm saying that right. Here's the gravity, sorry, one sec. Yeah, that is the gravitational little, so yeah, they may have said that g is equal to the acceleration due to gravity, but really, what it is, they always lie to you in life, so it's actually the gravitational field strength. Okay, so therefore, when we put A is equal to G, we put it back into this equation, obviously what we get is F equals mg. Okay, and you can rearrange that to get the gravitational field strength, which is force over the mass. And you have to remember this force is what we've just looked at, and the force was F equals G m1 m2 over r squared. So if you want to work out the gravitational field strength of a planet, okay, near its surface, it would be F equals mg, so G equals F over m. So divide this by the mass, okay, so you get G is equal to big G m1 over r squared. Okay, so hopefully that makes sense. It's kind of quite simple really. Okay, so that's obviously you just need to be able to use that idea. Okay, I don't think it gives you that specifically as a formula on its own. Okay, so very kind of basic that. Obviously in this sense, another way of saying G is equal to F over m, you could say the gravitational field strength is the force per unit mass. In other words, force over mass, which is what that equation says there. Yes, obviously you need to be aware of that. Gravitational potential. Okay, now this one kind of is a little bit weird because a lot of people, for some reason, don't like the idea of gravitational potential. Gravitational potential is almost the same. You can almost think of it as the same as what else is there to do in the spec in the whole physics. So it's to talk about potential that we really looked at AS and A2. Well, that's more gravitational potential. Well, it's very similar to gravitational potential energy. Is very similar to gravitational potential, but there are a few key differences that you need to be aware of. Okay, now gravitational potential is actually defined as the work done per unit mass. In other words, V, which is generally the symbol they put for gravitational potential is known, okay, is known as the work done per unit mass. In other words, the work done divided by mass. And we know the work done is force times distance, so it's force times distance, or force times delta R, okay, over the mass, and that is equal to the gravitational potential. Now, in the formula sheet, they give another formula for gravitational potential as V is equal to minus G M over R. I think that's the word they use. Okay, so that is another formula that you can use. And obviously, you just need to be aware that this is the mass of gravitational constant, separation, gravitational potential. Now, how the hell did they get to that? Well, what they do, as I say, in this, a couple of them would maybe show that questions, okay? So it's just about combining the equations that you've got in your formula sheet, okay? Really, most of the time, just trial and error, but there are quite a few similar, or I think a better way of saying it is repetitive questions, okay? Now, we know that this F here, okay, is the force. That force, remember, is equal to G M1 M2 over R squared, okay? And this is equal to V, okay? So if we rearrange this to get F, okay, what we do is we times both sides by M, so for sake, V times M is equal to F times delta R, okay? Therefore, rearranging this equation, Vm over delta R is equal to the force, okay? And the force is equal to this gravitational force of attraction, okay? So therefore, what you would do is it'd be Vm over delta R is equal to G M1 M2 over R squared, okay? You times both sides by R, okay? Yeah, this is right. So you times both sides by R, okay? So let's get rid of the R on that side and reduce the power by 1, okay? And then you would divide both sides by the mass, okay? So obviously that will get rid of a mass on both sides. So therefore the potential will be equal to Gm over R. But here we've said it's minus Gm over R. And the reason for that is because of the fact that when we draw a planet, okay, we have these things called equipotentials, which basically an equipotential is a line of constant potential. In other words, so this dot is a planet, okay? And this circle that I've drawn around it, now it looks weird. I've got to draw a few more to stop it looking really weird. Okay, maybe that doesn't look so much better. But anyway, on this circle, if I haven't really drawn it that well, but you get the idea. Okay, all the point along the circumference of each circle is the same distance away. Well, obviously for different circles it's different, but if you choose one circle, any point on its circumference will be the same distance away from the planet. Now, if it's not, that's because I've not drawn this very well, okay? But that's the principle, okay? So when you're the distance, because the field towards this planet, okay, is made up of field lines which look something like this, okay? So as I say, this video, by the way, again, just mention it again for those people that just keep skipping. It's just for just a recap, okay? So if I'm doing anything here, you go, where the hell have you got that from? Either, probably might not pay attention, or the fact that I've gone over it in my other video, so I'm assuming that you're familiar with this. Okay, so anyway, the field lines go towards the centre of the planet, okay, and obviously at any point along this, okay, along this circle, it was the same distance away from the planet, so therefore these field lines, it'll be the same point along just a different field line, but all these field lines that are going, these arrows that are going straight to the planet, they're all the same, exactly the same. However, obviously you'll be on a different one, but they'll be the same distance away from the centre of the planet. Okay, so therefore, at any point on the circumference along each circle, it'll be the same gravitational potential. Okay, and just like the energy levels inside an atom, okay, you can almost think of it. It looks like it. We put the minus. Yeah, I think we had the ground state, it was at minus 230 eV. eV is just the electron volt, but you don't need to remember that. okay? Because you don't have a, well, you do actually, but that's a different video, okay? And the reason we put minus there, because the positive of that was the energy needed to ionise the atom for the electron to leave the inner shell of the atom, okay? So, similarly like that, but obviously in this case we're talking about gravitational potential. Is the potential energy needed to actually escape the gravitational force, okay, of the planet, okay? Now you could relate it to that equation and say, well, what's the gravitational potential to escape Earth, okay? Well, you'd use that equation, okay? And obviously that'd be a gravitational potential, so you can work out your energy, okay? And you could sort it from there. But as I say, this is just a recap, so hopefully that makes a bit of sense. Okay, you also need to be aware of the fact that the gravitation potential is equal to negative, G is related to the gravitational potential. G is equal to minus delta V over delta R, okay? And again, that is just a case of rearranging equations, okay? And for that specific one, yeah, so going from this equation up here, we've got the gravitational potential is equal to the work done over the mass, and as we said, that was equal to the force times its distance over m, okay? Yeah, okay. Now, this part here is what I'm interested in, the force over the mass, okay? Force over mass is the same as saying, it comes from the equation F equals mg, okay? Force over mass we've got here is equal to the gravitational field strength, okay? So you replace F over m there with the g, okay? So therefore it becomes V is equal to G times delta R, okay? So therefore, if you wanted to work out G is equal to V over R, and remember it's a you put a negative there, okay? That gets you your gravitational field strength, okay? So you just need to be aware how you get that equation and how you get that equation, okay? But as I say, it's just this one is just they both come from rearranging the gravitational potential equation of work done per unit mass. Remember, work done. Gravitational fields, we can apply it to magnetic as well. Okay, so hopefully you understand that. Right. Now this thing here, I was saying that the magnetic flux density is basically just one unit of area. This magnetic flux, okay, basically is labelled as sort of a circle with an eye going through it at an angle, okay? And it's called magnetic flux, okay? This magnetic flux density, it takes into account just one unit area, but this magnetic flux takes into account all of the area, okay? So it's equal to BA. In other words, the magnetic flux density times the area, okay? And generally this will be associated, this comes from, by the way, I just put the circle there just to represent an area that is focused on, okay? Generally you will see magnetic flux density kind of in transformers or something similar, okay? You get the idea, okay? So this is what we call magnetic flux. Now magnetic flux linkage, because, so trying to build this up for you. This magnetic flux density is the force, is sort of to do with the force, it's because obviously each transformer is going to be different, made of a different metal, so it's going to have a different magnetic flux density, but you're going to be putting the same current and it's going to be the same length of wire, for example. And this, so therefore we have to take into account the actual qualities of the transformer, or more specifically the metal it's made of, okay? I know it will be soft iron core, etc., but generally they will be, but that's just confusion here. Magnetic flux density just takes into account, well, if we looked at one unit of area, okay, what would the force look like in that one little bit of area? And that's what that's taking account of. But this magnetic flux is saying, right, now we need to consider all of the area now, okay, which is BA. However, there's something else called magnetic flux linkage, which says, And that's all really nice, but I'm going to take it one step further. I'm going to say, let's look at the number of coils in that transformer now. And it's labelled as N, this by the way is labelled as phi, so it's N phi, which is NBA. Now that's not the basketball thing. I'm not even sure it is, I'll probably just kill myself now before I get tagged. This is called total magnetic flux linkage, or total flux linkage, okay? So they may say that, just to try and confuse you, flux linkage. Okay? Yeah. So hopefully that makes sense. But as I say, this will either be in the context of a transformer or an electric motor. Okay, I just put a transformer there because of this N thing. Okay, but they could look at it in the context of a electric motor. Okay, something like this. We've got two. So basically, what this is a bit of wire that spins. Okay, and these are two, this is a positive and a negative magnet. So what we've got here is a current and it intersects the electromagnetic field, which is what we're going to go on to look at in a little bit. Okay, and is this right from here? Yeah, when this, because we'll have field lines here, we'll have field lines going through the magnet, okay. This magnet will be, this, oh, God's sake, this bit of copper wire will be at certain angles to this field. Okay, now I talked about Fleming's left hand rule being at 90 degrees, but that's when it's at maximum, really, okay? So therefore, if it's at a maximum, just make sure this works. Sorry, one sec. Sorry, one second, let me just double check something out. I mean, I know how to explain it, but I just want to see if there's a better way to explain it to you. Okay, so what I've drawn on the board here is basically just the force between two charged objects. Okay, so it's very, very similar to Newton's law of gravitation, but obviously this is Coulomb's law, so there are a few differences. Now, as I say, principally the gravitational constant replaced by the constant in the electric field, which is 1 over 4 pi epsilon naught. Now, epsilon naught is given in the formula sheet. So, some people say, well, you could remember this. I think it's something like 8.85 times 10 to the minus 12 or something stupid. I would just simply work that out on the day of the exam. It takes 2 seconds, and if you try to remember it, you're likely to get it wrong, of course. So, I would simply just remember that, okay? So, the actual formula is K Q1 Q2 over R squared, but because K is 1 over 4 pi epsilon naught, the actual force is equal to Q1 times Q2 over 4 pi epsilon naught times R squared, okay? Where R is the general meaning of the difference between them. Now, unlike Newton's law of gravitation, this can be either attractive or repulsive. Obviously, if the two charges are the same, positive, they're both positive, then they're going to repel, okay, obvious basic stuff, okay, so hopefully you can see how that is. Not necessarily how it repulses, but you can just think, well, logically it's to do with electric field, so it's going to be either repulsive or attractive, okay, whereas in gravitational it's always attractive, okay, but anyway, I'll recap all these as we go through, okay. So electric field strength, again, this is very similar to the idea where I said F equals mg, okay, but obviously in gravitation we replace m with q and g with e, because this is the gravitational field strength, so we look at the electric field strength, and that's labelled as big E, okay? So F equals QE, or F equals EQ, whatever you want to look at it as. And remember, this Q is the charge, like this is the mass. This is the electric field strength, as though this is the gravitational field strength. So if you wanted to work out the electric field strength, it's F over Q, or in other words, force per unit charge. Okay, so that's the electrical field strength. Okay, Also, the actual field strength is also stated as being E is equal to V over D, where this is generally applied to the case where you've got, say, two plates, okay, and you look at the potential difference, so you look at the distance between them, the potential difference, and you can obviously work out the electric field strength. Okay, so basic applications there. But as I say, just really need to be aware of the formulas. So E equals F over Q, okay, where Q is the charge, E is the electric field strength, F is the force, okay, and then obviously just be aware of Coulomb's law. Okay, now if it asks you for the definition of Coulomb's law, you basically answer it in the way you would answer a gravitational Newton's law of gravitation question. Okay, so you say, well, the force is directly proportional to the sum of the charges, and it's inversely proportional to the square of their separation. But obviously, you need to state the fact that obviously the constant proportionality is different. Okay, which is k. You have to state what that is equal to, and then give the answer to that. Okay. So very, very basic, kind of just applying numbers to the formulas and rearranging them if you need to, and obviously you might have to be combining them, but as I say, you know, very rarely you will have to combine them. It's in the harder level questions, okay? So, you know, if you do get a question asks you to combine F equals QE with E equals V over D, you know, making that equal to E, okay, so we've made this equal to E, so E is equal to F over Q, actually I've stated up there, and we know E is equal to V over D, so if E is equal to V over D and E is equal to F over Q, then you can say V over D is equal to F over Q, and it might ask you, you know, to show something, so just be aware, very, very basic idea, rearranging equations and sub them in. Suddenly you can sub that one into F, okay, but as I say, don't need to worry about that. If I've just confused you there, you can just simply ignore that, because I think it's probably better and easier to answer it when we've actually got a question. And to be honest, shorthand is, I'd like to say I'm trying to make this video nice and short so I don't include any questions. But if I'm really truthful with you, can't be bothered in this video. Okay? Because I'll probably invent something. But no, I can't be bothered. That is slightly true. But I mean, the more of the reason is probably I'll get something wrong and confuse you even more. So whichever way you want to look at it, I'm assuming you probably just look at it as a lazy bitch, but it's up to you, it's fine. Okay, right. So, that's electric field strength. The next thing it mentions is electric potential. Now, again, this is very similar to gravitational potential, okay? So in gravitational potential, we said the gravitational potential, which is labelled as V, okay, is the work done per unit mass. Now, we're still going to use V, because still represents potential, okay? However, it's not work done per unit mass, because I remember in anything to do with electric fields, we replace mass with charge, and obviously the gravitational constant with the constant for electric fields, which is that 1/4 pi epsilon naught. So it's not work done per unit mass. In other words, it's not work done over mass. It's work done per unit charge. So it's work done divided by charge. Okay, so again, just rearranging that equation, okay? You could say work done, W equals QV, and manipulate it just like you did with gravitational fields. Okay, so remember we said the work was equal to F times delta R over Q, okay? And remember we said the F was equal to K Q1 Q2 over R squared, obviously K is at 1/4 pi epsilon naught, and then just a case of rearranging it from here and where you want to go. Now obviously you have to also remember that F is equal to QE, okay? So just combining, if you want to combine this equation with that one with F over Q, or if you want to rearrange this equation to get it in terms of F and then sub this equation in, okay? So as I say, it's up to you, you know, just like we did with the other one, okay, where we got V is equal to M over R, okay. Instead of getting Gm over R, G is a gravitational constant, so we replace that with K, okay, or 1/4 pi epsilon naught, okay, and we replace the M with Q, okay. So therefore, when we do that, we get V is equal to, well, I'm just going to put K in, but remember K is equal to that Q over R, and it may ask you to prove that, okay, in which case you just sub this equation into that or that one, just see what works, okay. So I've gone through that very quickly. That's because we've gone through gravitational fields and it's very, very similar. So I know it's not specifically when it mentions in the spec the differences and similarities about the fact that it subs in the mass for charge and obviously the gravitational constant with the electric field constant. But you can see how just applying that one simple idea, how you can basically understand one type of field and then just apply it to the other. Now, as I say, there are varying differences, and I keep mentioning this, but you know, it's just very, very similar. Okay, so that's pretty much all there is to do with electric fields. Now, the comparison here, okay, so because it might ask for a question, you know, the 6 marker or 4 marker or whatever, it might say what are those, compare the similarities and the differences. Now, obviously, if it's a 6 mark question, you're likely to having to do something else. So when you simply just comparing, you know, stating 2 similarities, 2 differences, it's likely to only be a 4 mark question. We'll say only, still a big part of the exam. Okay, so I'll just list a few for you here. Okay, so the similarities, well, they both have the inverse square law. Okay, you could say that. So I've got over here similarities. They both use the inverse square law. So that's the, you know, directly in proportion. Inverse proportional to the square of the separation. They both use that. Okay, so that's called the inverse square law. The fields, okay, now I haven't gone through it specifically in this one, but they both exhibit radial and radial fields. They both exhibit equipotentials, so any one of them, just like equipotentials. Okay, however the difference is, the main one that I've stated really, is the fact that gravitational fields, gravitational forces, is always attractive. Okay, whereas obviously the electric field is not always attractive. It can either be repulsive or attractive. Okay, so they're just a few, but as I say, I'm only going through a few things in this video. Okay, so they're just a few similarities and differences between the 2 fields. But as I keep mentioning, because I think it's so important, they replace mass with charging. Obviously the 2 constants are different. But the rest of it is very, very similar. Okay, now if you do have this AQA book, so you know the one, okay, there is quite a bit extra, okay, in terms of it mentions about planetary fields, which is, well, actually no, there's just a few extra bits in here in terms of, gives you a bit notice about potential gradients. Actually is one thing. So potential gradients is delta V over delta R. It's the change in potential over the change in distance that you've moved, okay, which is the same for electric and gravitational fields. So it's just stuff like that that is extra mentioned in the book, and anything to do with that I have done in the playlist for Unit 4 and 5, so check that out. But if it's not up yet and you do want a bit of information about it, because I probably haven't done a good enough job in this video, please do leave a comment and I'll obviously try and get back to you. Okay, so that's all really to do with fields, and it is quite a common part of Unit 4 that people really don't like, but I don't think it's actually that bad. I mean, you know, obviously the electric and gravitational fields is where people, yeah, so it's really electric fields I think people find generally difficult, but you can just think of it as being the same as gravitational, okay, but replacing mass with charging obviously the 2 constants as I mentioned. I think the other thing that is quite difficult is simple harmonic motion, so make sure you know the differences, make sure you know the principles of it and that graph, okay, I was going through, and then the equations, okay, just be familiar with the equations, okay. But as I say, there's nothing too challenging at all, and obviously momentum is so easy, you probably did most of that GCSE anyway. Okay, so the next is about capacitance. Now, this I don't like. Well, I do like this topic, but I think the first little bit that you need to be aware of is quite a bit of a, which it's not difficult, but it's a bit of a mouthful. I think that's a bit right way of saying it. I think saying mouthful, right? Okay, so we have this thing in capacitors called capacitance because, well, we need to compare. Yes, there are different capacitors, are different material, different types, different, you know, how good they are at holding charge. But that how good they are at holding charge is different for each capacitor. But obviously they can still hold the same amount of charge. They can still hold have a potential difference across them. So the only way to differentiate for one capacitor to another is come up with this idea of capacitance. It's, as I say, essentially how well can the capacitor hold charge per unit of potential difference. That's the right way of saying it, yeah. Okay, so therefore capacitance is potential, potential difference there. Charge over potential difference is how well it can hold that charge over a given potential difference. Now, you don't have to think of it like that. You just simply think of what that equation says. Now, this C is capacitance. It's measured in farads. Okay? Or, what I like to do, because there are certain things in physics that it's trouble remembering their specific units. Okay? Just remember the units of the object of this, which charge, obviously coulombs, and volts is obviously, potential difference, which is measured in volts. So you could either say it's measured in farads, or because of this equation you could say it's coulombs per volt, in other words CV to the minus 1. Okay, so either of them two would be the units for capacitance. I say it's better putting that because it shows you a bit, you've remembered the unit, but if you do forget them on the day of the exam, you can just use them. As I say, basic indice rules and the what you measure charge and potential differences in, okay? Difference in, okay, and just apply it to that question. Now, as I say, you may be asked to manipulate that question, etc. Now, I just want to rewrite this question actually, because because the next bit is asking about energy stored. Now, if we rewrite this question as Q is equal to CV, in other words, times both sides by a potential difference, okay, what this says here, now this capacitance, remember, as I say, it is principally how we differentiate one capacitor to that of another capacitor. Okay, so for all capacitors, the charge will be directly proportional to the potential difference. Okay, because the more charge they have, the more potential difference they will have across them. Okay, but how much potential difference they can store for each unit charge, okay, is different, okay, for each capacitor. Okay, so therefore we say a constant of that is the capacitance. So therefore the constant proportionality is C. So therefore this implies a graph of charge against potential difference will have a constant gradient of C. Now you could, if that doesn't work for you, you could relate this, Q equals CV, to the graph of Y is equal to mx plus C. Now obviously there's no plus C bit here, but because that plus C equals 0, so they've just not included it. Okay, but say if we drew this graph here of charge, which we're measuring Q, against potential difference V, it should go through the origin and have a straight line. A line with a constant gradient. Now the thing that you might get asked is either what does this area under the curve represent, or how to calculate the energy. Now, kind of giving the answer away there because I've said the two different things that you might ask, and it doesn't take a genius to work out. I'll give you the answer. This area, as I mentioned, is the energy stored in the capacitor. Okay, so I don't think there's any other way of building up to that apart from just telling it you. So, as I say, it's just something, just one of them things you've just got to remember. Okay, so how do we work out the area of this? Well, you can just say E is equal to a half of Q times V. Okay, and that's the energy stored in a capacitor. Okay, so very, very easy to understand. Now there are because we've got this equation here, Q equals CV. Okay, and obviously you can rearrange that to get V. You can rearrange it to get Q. Now there's no point rearranging it to get C, because the whole purpose of rearranging that equation is to put it into this energy equation, which you can then manipulate. In other words, because we know Q is equal to CV, and we've got E is equal to a half of QV, this Q can be replaced by CV, so it's a half times what we'd normally see is Q, we'll put CV, so a half times C times V times V, okay, because we've got V on the outside as well, so it'd be half of CV squared, okay, and that means exactly the same thing, because all we've done is worked out the area under here, and then used this equation and subbed it in to Q, and obviously rearranged that equation, okay, but there are other manipulations of that. Okay, so I'm just waffling on, I'm boring myself, so I don't know what the hell I'm doing to you. But it's just basic manipulation, it's very easy. Okay, maybe you don't find it easy, but you know, stuff. Okay, so that's energy stored by a capacitor. Now, the next bit is the main part of capacitors, and the thing you're most likely to be asked on. Okay, now, I'm going to give a bit of an explanation to this curve. Now, because this idea about capacitors discharging, okay, and the equations that we're going to come up with here, I'm going to show you, it only works for discharging capacitors. That's crucial. Because this is going to give an exponential curve, obviously you know that, okay. It only works for discharging capacitors, and hopefully it kind of, I'll just go over why that is. But say we've got the charge here and we've got the time. Okay, so this is, I mean, if it doesn't look so exponential, that's because my drawing is shit. But it's meant to be an exponential graph, okay? The reasons behind that, well, we've got a continually changing gradient here, and in this case it's continually decreasing gradient, okay? It's slowly getting from really extreme to zero. Well, actually no, that's going to be increasing, sorry, I do apologise, okay? But anyway, it's getting close to zero, the gradient's changing. And that's well, you can see in this instance here, initially, there's a great difference for each little bit of time we go across the x-axis, or the time axis, whatever you want to call it. There's a huge change in the difference in charge, okay? But then as we get past here, about here, I think it is if you measure it up, it starts to get lower and lower and lower. In other words, we need more bits of time, if you can imagine bits of time, to get rid of the same charge, okay? So what we've got here, as I say, is, well, I've just explained it and then explained it again, so it's kind of thick. Yeah, and that's because in a capacitor, let me just make sure I've still got enough time on the clock here. Yep. Okay, sorry about that. Right, so as I was talking about, this is an exponential curve. Now, what I've drawn here is just kind of a very basic analysis of what a capacitor inside a capacitor, what it might look like, okay? So, all these circles here, what the meant to represent is just a build-up of charge, okay? So, remember, one of the things you need to be able to state is that a capacitor, all it does is just, if it says define a capacitor, or something similar, you could just say it's just an electrical component inside a circuit that holds charge, okay? And it's key to remember, obviously all these electrons, well, they're not going to be different, they're all the same because it's current flowing through the capacitor, okay? And current is the flow of charge, the flow of electrons, okay? So all these electrons are going to have exactly the same charge. But if we put two positives, or in this case, both negatives together, they're going to want to push each other apart. So initially, when we say yes, we're going to allow that, okay? So, because obviously if they want to push each other apart, but they've got nowhere to go because we've closed the capacitor in terms of we've not connected it, we've not allowed it to discharge because, well, it's going to want to discharge, but we keep adding, we keep passing current through it to keep building up the charge, but it will, if we stop the current, all of it would eventually go. However, initially, the rate would be very high because you've got a lot of electrons there. So each electron is repulsing the other electrons, if you can imagine it like that. So the more electrons we have, the greater repulsive force there will be in the capacitor, okay? So bigger force means more of them will be moved out more quickly, okay? So initially, there's a great discharging, a huge rate of change of charge within the capacitor, okay? but then as there's less remaining, the force pushing them out is less, okay? So there's going to be a lower amount of electrons inside the capacitor, okay? So that's why the rate of change of charge begins to kind of die off, because there's not that force there pushing them out, okay? So hopefully that kind of explains why that is. Right, one thing you need to be aware of is something called the time constant. Now the time constant is calculated by RC, okay, and that's equal to something called the time constant. Now before I just mention what the time constant is again, just to make sure you're aware, R is the resistance of the capacitor, the resistance of the circuit. Generally it's just a capacitor, okay, so it's resistance of the capacitor, and C is the capacitance of that capacitor. Remember, C comes from the equation Q equals CV, okay, and the capacitance comes from that rearranged, okay. That is equal to the time constant. What does the time constant actually show us? Well, it actually shows us, because we're looking at the decrease here, okay, this time constant will generally only be associated with the decrease. It's the amount of time that it takes for 33% of the charge to disappear. So when 33% of the charge has disappeared, the time that takes is equal to 1 time constant. Now because this is not linear, okay, you just need to be aware that to totally discharge the capacitor, we need 5 time constants. To fully discharge. Okay? So that's equal to what time constant is. Now, just like when we were looking at the... Oh, God. What was it called now? Sorry. When you look at you can relate these two equations, so you can relate the nuclear radioactive decay, which is also exponential, and the decay of the, the discharge of the capacitor. Now the discharge of the capacitor equation, Q is equal to Q naught times e to the negative, e to the power of T over RC. So when T equals RC, you may go, well, why is it 33%? Okay, and the reason it's 33%, well, if you put it into this equation here, Q is equal to Q naught e to the power of T over RC. When T equals RC, okay, you get e to the power of, it's minus T over RC. Yeah, sorry, it's e to the power of minus T over RC, sorry. So when this T is equal to RC, you get Q times e to the power of minus RC over RC. In other words, e to the power of minus 1. And if you do e to the power of minus 1 in your calculator, you get 0.33. Okay? And what you're doing there is timesing Q by 0.33. Okay? So therefore, that's when the time is equal to the time constant, 33% of the charge is gone. Okay? So that's why, and obviously this is exponential, so it's not going to be simple ratio. Okay? So that's why we can follow this curve. Okay? So hopefully that makes sense. Right. Yeah, you should also be aware that we can apply this because Q equals IV, etc. We can apply this to V equals V naught e to the times e to the negative T over RC. We can apply this to the current, I is equal to I naught times e to the power of T over RC. And you have to be aware that this I naught or Q naught or V naught, that's the initial, whatever it might be. So that's the initial charge, the initial potential difference, the initial current, etc, etc. And this, the end, the IQ, VI and Q, okay, in this case, that is the period of charge that is gone after whatever time you put in. Okay? So again, it's just about equations and manipulating the equations. Okay, so that's the end of capacitance. That's really the crux of it. Okay, so if you get that, you're totally okay. You don't have to worry. Right. Okay. So the next thing we're going to go on to is it's quite. I think personally, apart from SHM for me, I think this is probably the hardest part of Unit 4 because I don't think the electric and gravitational fields are actually too bad. It's just a case of knowing what potential is, and knowing what knowing forces, what the difference is between gravitational and electric. I think, along with simple harmonic motion, which actually generally, really, realistically speaking, isn't that difficult, it's the questions that are difficult. I think this topic is, this bit here is the hardest bit to understand. And it's a start, and the reason for that is to do with magnetic fields. So we're not looking at electromagnetic, although we are going to be looking at a bit about that, but in a sense we're not looking at electric fields or gravitational, this is magnetic. Okay? Now, there's something called magnetic flux density. Okay? And actually, to start off, before we go into that, just familiarise yourself with Fleming's left-hand rule. Okay? So, our thumb, Manchester. Okay, so obviously that is my hand there, which is crazy. Thumb, that represents the motion. This is the first finger, that represents the field, and the second finger represents the current. The whole purpose of that is just to show that the current is at 90 degrees to the field, and the motion, or the force, this represents the force, we'll label this as F, but in Fleming's left-hand rule, it's known as the motion, but really, when we're going to look at this, we're looking at the force. That's the field, that's the current, okay? So, the whole point of that is just to show you the relationship between, there's 90 degrees between the current and the field, and there's 90 degrees between the field and the force, or the motion. Okay? So, I actually don't need to draw that on, but I hope you get the idea. Now, this force bit of the thumb is what we'll be looking at. Okay? And that force is equal to BI times L. I, obviously you know, is the current. L is the length. But B is this magnetic flux density. Magnetic flux density. Now, there's no specific definition for that, apart from the fact, obviously it's measured in Tesla, and really it just comes from the rearranging of that equation. Now, the way I think of it, because it's going to help us to understand total magnetic flux linkage, what generally associated with, say if we've got a horizontal plate here, so it's just one that's bounced like that, okay, this here, these are force lines acting downwards on a plate, okay, and this could be because it's intersecting the magnetic field, okay, and this is just the magnetic field lines pushing down on it. One of these field lines is B, okay, and it'll make sense. Basically, that magnetic flux density is just one of these field lines, okay, just one of them. And I'll explain why, okay, so it's one unit of area of these field lines, because that's probably a better explanation, okay. So, I'll go into a bit more about that. Well, obviously, I've done it properly in my video, but I'm assuming some of the people who are watching this probably haven't been bothered to watch that video. So, I'm trying to build it up in the sense that you know what you're doing, going through your specification, and just a bit of a recap on certain things I think are a bit more important, okay. So, you can think of that as one unit area, okay, of a field line. Okay, acting down. That's what magnetic flux density is. You won't get a definition on it as such as the definition of magnetic flux density. I don't think it doesn't say really. So remember, this force is coming from that motion in Fleming's left-hand rule. Okay, and it could be this force could be in the sense that if we've got a let's say this is a cloud chamber, for example, and we've got an electron entering this cloud chamber. These dots represent the path of the electron, okay? If these are the field lines, the force, okay? The field is pointing down, okay? It will cause the electron, okay, as a current to bend to the right, okay? So that's just a bit of, sorry, not very good. I mean, you get the idea, okay? And the force on this electron, because we have to take into account the charge, is F equals BQV. See if I've just got an explanation for that. Okay. Oh, by the way, this electron moving in the cloud chamber in the field, where there's field lines pointing down, okay, it's called, the force acting on it is F equals BQV, and that is given in the formula sheet. But because it's it's going in an arc, and if you carried that arc round, obviously you'd end up in a circle. We can say that this FB is equal to BQV is equal to F equals mv squared. So mv squared equals BQV. And obviously you could rearrange that equation to work out whatever you wanted to. Okay? So just be aware of that. Okay, so remember this is just in a cloud chamber where the field is acting downwards, it causes the electron, because the force acts at right angles to the field, okay, it will go down, go at 90 degrees to the field. Okay? So therefore it's going in a circular path, we can apply circular motion to it. Okay, so just like we could apply circular motion to sorry about that, I just had a bit of a rethink. I think this is a bit better explanation. So this is basically an electromotor. Now I did have them two magnets at the side, but I've kind of got rid of them. Theoretically they would be there, I've just focused on the magnet in the field lines. Okay, now this total flux linkage, okay, is actually not just NBA, it's yeah, you could obviously write MBA as BAN, so I have done here, I've just wrote the letters the other way around, but obviously it doesn't make a difference. Okay, and this total flux linkage is a maximum when cos theta is a maximum. And this theta, this angle, okay, is the angle between the horizontal of the magnet, okay, to the normal of the field line. Okay, and when the angle is either, say, 0 or 360, this will give the maximum value of 1. Okay, so obviously that's the answers there. But as I say, that'll be more obvious when you actually do a question on that. But seeing as this isn't, as I say, this video is just simply an overview of the types of what you need to know. Okay, so anyway, that's just a little bit on that. And that's really all there is to flux linkage and magnetic flux. Okay, this next part goes off onto something called electromagnetic induction. Okay, now it says in the specification that you just need to be able to explain how, well, it says simple experimental phenomena. Basically what that means is you need to explain how what exactly is electromagnetic induction? How does it occur? What do we mean by it? Well, electromagnetic induction is simply just creating electricity through combining electric fields and magnetic fields, hence electromagnetic induction. What essentially happens is, say we've got a magnet, okay, so we've got north and south on it, and then you'll have, generally it'll be a coil, okay, and you'll move this magnet in and out of this coil, and basically what will happen is this magnet will have field lines obviously on it, something like that, okay, and when it goes through the coil, okay, there are already electrons inside this coil, because it's metal, they're free electrons so they can move, and when the magnet is put through the coil, okay, it moves the electrons out of the way, okay, in order it intersects the magnetic field of the, it causes the magnetic field in the magnet to intersect the electric field of the coil, okay, because there's free electrons, so technically it is an electric field, and it induces something called eddy currents. And basically these are just currents that are induced by electromagnetic induction. Induces eddy currents. Okay, so basically, as I say, what happens is the magnet is put through the coil, okay, forcing the electrons out of the way, and as it forces the electrons out of the way, they move, causing a flow of charge, inducing an eddy current. Okay, that's just a word. Eddy current is just a word that used to describe currents which are generated through electromagnetic induction. Now you can speed this up, you can have a greater current by either increasing the strength of the magnet, increasing the number of coils, or moving it faster. Okay, I think actually the main two are moving it faster, in and out faster, without sounding weird, and having a stronger magnet. Basically a bigger magnet with more pronounced field lines. Okay, the next is about Faraday and Lenz's law. Now I say Faraday and Lenz's law, it's really Faraday's law and then Lenz just add a bit to it. So you could argue it's both. What he says, so we get his wording. Oh, by the way, yeah, if you wanted to make that faster, if you wanted to increase the eddy current, you could also do it in reverse. That's another way to increase it. Now we know that flux linkage is n phi, which is equal to nba cos theta, which is what we just looked at previously. Okay. Now, what Faraday said was that his law of electromagnetic induction, I'll read it out for you, states that the induced EMF in a circuit is equal to the rate of change of flux linkage through the circuit. Okay, so the EMF generated in this coil, okay, is equal to the rate of change of this. So it's the rate of change. So it's n phi. Okay, so flux linkage, change in flux linkage over the change in time. That's the EMF. Okay. Now, as I say, this gives it gives a cos graph. This, okay. The flux linkage gives a cos graph, as we've proved here with cos. So, as this is a rate of change of magnetic flux linkage, okay, this is a rate of as I say, it's a rate of change of magnetic flux linkage, which is a cos graph. So it's a rate of change of a cos graph. In other words, you differentiate is the gradient of cos, or the differential of cos, okay, because we know the differential is a gradient function, so it's a differential of a cos graph, which gives a sine graph. So therefore this implies that the induced EMF will give a sine graph. Okay, so hopefully that makes sense. Okay, so hopefully you get why that is. Right, okay, so, oh yeah, and Lenz's law, he just said that the current which is produced is going to the opposite way it changes, okay? So basically, the Lenz's bit, he just added a minus in front of this rate change of flux linkage, okay? Now, as I said, it's a rate of change of this curve, so of this graph, okay? So you could say that EMF is equal to, because this n phi is the same as saying n times nba cos theta, okay? We've just wrote n phi here. We could have wrote nba cos theta, okay? So, as I say, the rate of change of this is going to give a sine curve. Now it's still going to be NBA, it's just going to be NBA sine theta, okay? However, it's going to be a little bit more than that, okay? So it's BAN, angular speed, times the sine of the angular speed times the time. That's the EMF equation, and it's not given in the formula sheet, it's something you just need to remember. Okay, and I don't think there's any other way I can kind of introduce that to you without confusing you. Okay, the last little bit of Unit 4 is about transformers. Okay, and I don't really think you need to know that much, to be honest, because my video does a pretty good job at that. You just need to be aware of the transformer equations, okay, and the fact that they obviously wouldn't have mentioned at GCSE about the transformers having a soft iron core, so that because what happens there is the electric fields intersect the magnetic fields, okay, and if we have a soft iron core, they can cut through the field lines more quickly, okay, so they need a higher magnetic flux density. Okay, but as I say, didn't really do very much on that at all, because I go through it very quickly in my tutorial for that anyway, so it's very, very simple. I don't really think I'd go too much into it, and to be honest, you can just go on a specification online. Now if you do want a link to that because you can't find it on the AQA website for some reason, please do comment below, or you can inbox me if you don't want to be embarrassed, and I'll just send you the link to it, because it is a little bit weird to find. I do admit that on the website. Okay, so again, if you have any questions about anything we've done, it's finally the end, it doesn't feel like it, but well, you've made it, so I can say, so well done. But very kind of simple, and I will be going through Unit 4 past papers very soon, but before I do that, I think I'll probably finish off the Unit 5 overview. Now just to reiterate, for the Unit 5 overview of the specification, what I'll be doing is I'll be doing it in 2 parts. Okay, so I'll be doing Unit 5, which everyone does, the thermal physics. Okay, and unfortunately I'll only be doing the overview of the specification for astrophysics, and that's really because I've only really done astrophysics, to be honest. I could look at the other parts of the specification, the other options, but to be honest with you, I probably would only be just simply saying what's on the specification and going over any bits that I think you might need to be able to be aware of. But as I say, I'll do that over the summer if I do, so it'd be pointless for you, to be honest, because I've obviously got other exams and stuff. So basically stuff you and we'll work out something. Okay, but if you do want me to go over, if you do really want me to go over some of the other options very quickly, I'm more than obviously happy to do that. But just, feel guilty about it, obviously. Joking, don't. Alright, so thanks for watching, and hopefully it's been helpful. See you in the next video.